A shield volcano is a type of volcano usually built almost entirely of fluid magma flows. They are named for the large size and low profile, resembling a warrior's shield lying on the ground. This is caused by the highly fluid lava they erupt, which travels farther than lava erupted from stratovolcanoes. This results in the steady accumulation of broadsheets of lava, building up the shield volcano's distinctive form. The shape of shield volcanoes is due to the low viscosity magma of the mafic lava. Etymology: shield volcanoes are built by effusive eruptions, which flow out in all directions to create a shield like that of a warrior. The word shield has a long history, and is derived from the Old English sealed, which is in turn taken from the Proto-Germanic *skeldus, and related to the Gothic skildus, meaning to divide, split, or separate. Shield volcano itself is taken from the German term Schildvulkan. Geology: structure: shield volcanoes are distinguished from the three other major volcanic archetypes, stratovolcanoes, lava domes, and cinder cones, by the structural form, a consequence of the unique magmatic composition. Of these four forms, shield volcanoes erupt the least viscous lavas, where stratovolcanoes and especially lava domes are the product of highly immotile flows, and cinder cones are constructed by explosively erupted tephra. Shield volcanoes are the product of gentle effusive eruptions of highly fluid lavas that produce, over time, a broad, gently sloped eponymous shield. Although the term is generally ascribed to basaltic shields, it has also at times been appended to rarer scutiform volcanoes of differing magmatic composition, principally pyroclastic shields, formed by the accumulation of fragmental material from particularly powerful explosive eruptions, and rarer felsic lava shields formed by unusually fluid felsic magmas. Examples of pyroclastic shields include Billy Mitchell volcano in Papua New Guinea and the Purica complex in Chile. An example of a felsic shield is the Big Obsidian flow in Oregon. Shield volcanoes are also related in origination to vast lava plateaus and flood basalts present in various parts of the world. Generalized eruptive features which occur along linear fissure vents and are distinguished from shield volcanoes proper by the lack of an identifiable primary eruptive center. Active shield volcanoes experience near-continuous eruptive activity over extremely long periods of time, resulting in the gradual build-up of edifices that can reach extremely large dimensions. With the exclusion of flood basalts, mature shields are the largest volcanic features on Earth. The summit of the largest subaerial volcano in the world, Mauna Loa, lies 4,169 meters above sea level, and the volcano, over 60 miles wide at its base, is estimated to contain about 80,000 cubic kilometers of basalt. The mass of the volcano is so great that it has slumped the crust beneath it a further 8 kilometers, accounting for this subsidence and for the height of the volcano above the seafloor. The true height of Mauna Loa from the start of its eruptive history is about 17,170 meters. Mount Everest, by comparison, is 8,848 meters in height. In September 2013, a team led by the University of Houston's William Sager announced the singular origination of Tamu Massif, an enormous extinct submarine shield volcano of previously unknown origin which, approximately 450 by 650 kilometers in area, dwarfs all previously known volcanoes on the planet. The research has not yet been confirmed. Shield volcanoes feature a gentle slope that gradually steepens with elevation before eventually flattening near the summit, forming an overall upwardly convex shape. In height they are typically about 1/20th the width. Although the general form of a typical shield volcano varies little worldwide, regional differences exist in the size and morphological characteristics. Typical shield volcanoes present in California and Oregon measure 3 to 4 miles in diameter and 1,500 to 2,000 feet in height. Shield volcanoes in the central Mexican Michoacán Guanajuato volcanic field, by comparison, average 340 meters in height and 4,100 meters in width, with an average slope angle of 9.4 degrees and an average volume of 1.7 cubic kilometers. Rift zones are a prevalent feature on shield volcanoes that is rare on other volcanic types. The large, decentralized shape of Hawaiian volcanoes as compared to the smaller, symmetrical Icelandic cousins can be attributed to rift eruptions. Fissure venting is common in Hawaii. Most Hawaiian eruptions begin with a so-called wall of fire along a major fissure line before centralizing to a small number of points. This accounts for their asymmetrical shape, whereas Icelandic volcanoes follow a pattern of central eruptions dominated by summit calderas, causing the lava to be more evenly distributed. Asymmetrical, eruptive characteristics. Most of what is currently known about shield volcanic eruptive character has been gleaned from studies done on the volcanoes of Hawaii Island. By far the most intensively studied of all shields due to the scientific accessibility, the island lends its name to the slow-moving, effusive eruptions typical of shield volcanism, known as Hawaiian eruptions. These eruptions, the calmest of volcanic events, are characterized by the effusive emission of highly fluid basaltic lavas with low gaseous content. These lavas travel a far greater distance than those of other eruptive types before solidifying, forming extremely wide but relatively thin magmatic sheets often less than 1 meter thick. Low volumes of such lavas layered over long periods of time are what slowly constructs the characteristically low, broad profile of a mature shield volcano. Also, unlike other eruptive types, Hawaiian eruptions often occur at decentralized fissure vents, beginning with large curtains of fire that quickly die down and concentrate at specific locations on the volcano's rift zones. Central vent eruptions, meanwhile, often take the form of large lava fountains, which can reach heights of hundreds of meters or more. The particles from lava fountains usually cool in the air before hitting the ground, resulting in the accumulation of cindery scoria fragments. However, when the air is especially thick with clasts, they cannot cool off fast enough due to the surrounding heat, and hit the ground still hot, accumulating into spattercones. If eruptive rates are high enough, they may even form splatter-fed lava flows. Hawaiian eruptions are often extremely long-lived. A cinder cone of Kilauea has been erupting continuously since 1983. Flows from Hawaiian eruptions can be divided into two types by the structural characteristics. Pahoehoe lava, which is relatively smooth and flows with a ropey texture, and air flows which are denser, more viscous and blockier. These lava flows can be anywhere between 2 and 20 meters thick. Air lava flows move through pressure. The partially solidified front of the flow steepens due to the mass of flowing lava behind it until it breaks, after which the general mass behind it moves forward. Though the top of the flow quickly cools down, the molten underbelly of the flow is buffered by the solidifying rock above it, and by this mechanism air flows can sustain movement for long periods of time. Pahoehoe flows, in contrast, move in more conventional sheets, or by the advancement of lava tows in snaking lava columns, increasing viscosity on the part of the lava as shear stress on the part of local topography can morph a Pahoehoe flow into an AA1, but the reverse never occurs. Although most shield shield volcanoes are by volume almost entirely Hawaiian and basaltic in origin. They are rarely exclusively so. Some volcanoes, like Mount Wrangell in Alaska and Cofre de Perote in Mexico, exhibit large enough swings in the historical magmatic eruptive characteristics to cast strict categorical assignment in doubt. One geological study of de Perote went so far as to suggest the term compound shield-like volcano instead. Most mature shield volcanoes have multiple cinder cones on the flanks, the result of tephra ejections common during incessant activity and markers of currently and formerly active sites on the volcano. One prominent such parasitic cones is on Kilauea. Continuous activity ongoing since 1983 has built up a 2,290 feet tall cone at the site of one of the longest-lasting rift eruptions in known history. The Hawaiian shield volcanoes and the Galapagos Islands are unique in that they are not located near any plate boundaries. Instead, the two chains are fed by the movement of oceanic plates over an upwelling of magma known as a hotspot. Over millions of years, the tectonic movement that moves continents also creates long volcanic trails across the seafloor. The Hawaiian and Galapagos shields, and other hotspot shields like them, are both constructed of oceanic island basalt. The lavas are characterized by high levels of sodium, potassium, and aluminium. Features common in shield volcanism include lava tubes. Lava tubes are cave-like volcanic straits formed by the hardening of overlaying lava. These structures help further the propagation of lava, as the walls of the tube insulates the lava within. Lava tubes can account for a large portion of shield volcano activity. For example, an estimated 58% of the lava forming Kilauea comes from lava tubes. In some shield volcano eruptions, basaltic lava pours out of a long fissure instead of a central vent, and shrouds the countryside with a long band of volcanic material in the form of a broad plateau. Plateaus of this type exist in Iceland, Washington, Oregon, and Idaho. The most prominent ones are situated along the Snake River in Idaho and the Columbia River in Washington and Oregon, where they have been measured to be over 1 mile in thickness. Calderas are a common feature on shield volcanoes. They are formed and reformed over the volcano's lifespan. Long eruptive periods form cinder cones, which then collapse over time to form calderas. The calderas are often filled up by future eruptions, or formed elsewhere, and this cycle of collapse and regeneration takes place throughout the volcano's lifespan. Interactions between water and lava at shield volcanoes can cause some eruptions to become hydrovolcanic. These explosive eruptions are drastically different from the usual shield volcanic activity, and are especially prevalent at the waterbound volcanoes of the Hawaiian Isles. Distribution: shield volcanoes are found worldwide. They can form over hotspots, such as the Hawaiian Emperor Seamount Chain and the Galapagos Islands, or over more conventional rift zones, such as the Icelandic shields and the shield volcanoes of East Africa. Many shield volcanoes are found in ocean basins, such as Tamu Massif, the world's largest, although they can be found inland as well, East Africa being one example of this. Hawaiian Islands. The largest and most prominent shield volcano chain in the world is the Hawaiian Islands, a chain of hotspot volcanoes in the Pacific Ocean. The Hawaiian volcanoes are characterized by frequent rift eruptions, the large size, and the rough, decentralized shape. Rift zones are a prominent feature on these volcanoes, and account for the seemingly random volcanic structure. They are fueled by the movement segment of the Pacific plate over the Hawaii hotspot, and form a long chain of volcanoes, atolls, and seamounts 2,600 kilometers long with a total volume of over 750,000 cubic kilometers. The chain contains at least 43 major volcanoes. A major seamount at its terminus near the Ural-Kamchatka Trench is 85 million years old. The volcanoes follow a distinct evolutionary pattern of growth and death. The chain includes the second largest volcano on Earth, Mauna Loa, which stands 4,170 meters above sea level and reaches a further 13 kilometers below the waterline and into the crust, approximately 80,000 cubic kilometers of rock. Kilauea, meanwhile, is one of the most active volcanoes on Earth, with the current ongoing eruption having begun in January 1983. Galapagos Islands. The Galapagos Islands are an isolated set of volcanoes, consisting of shield volcanoes and lava plateaus, located 1,200 kilometers west of Ecuador. They are driven by the Galapagos hotspot, and are between approximately 4.2 million and 700,000 years of age. The largest island, Isabela Island, consists of 6 coalesced shield volcanoes, each delineated by a large summit caldera. Espanola, the oldest island, and Fernandina, the youngest, are also shield volcanoes, as are most of the other islands in the chain. The Galapagos Islands are perched on a large lava plateau known as the Galapagos Platform. This platform creates a shallow water depth of 360 to 900 meters at the base of the islands, which stretch over a 174 miles long diameter. Since Charles Darwin's famous visit to the islands in 1835, there have been over 60 recorded eruptions in the islands, from 6 different shield volcanoes. Of the 21 emergent volcanoes, 13 are considered active. Blue Hill is a shield volcano on the southwestern part of Isabela Island in the Galapagos Islands and is one of the most active in the Galapagos, with the last eruption between May and June 2008. The Geophysics Institute at the National Polytechnic School in Quito houses an international team of seismologists and volcanologists whose responsibility is to monitor Ecuador's numerous active volcanoes in the Andean volcanic belt and the Galapagos Islands. Locumba is an active shield volcano in Fernandina Island in the Galapagos that has been erupting since April 11, 2009. The Galapagos Islands are geologically young for such a big chain, and the pattern of the rift zones follows one of 2 trends, one north-northwest, and one east-west. The composition of the lavas of the Galapagos shields are strikingly similar to those of the Hawaiian volcanoes. Curiously, they do not form the same volcanic line associated with most hotspots. They are not alone in this regard. The Cobb-Eichelberg Seamount chain in the North Pacific is another example of such a delineated chain. In addition, there is no clear pattern of age between the volcanoes, suggesting a complicated, irregular pattern of creation. How exactly the islands were formed remains a geological mystery, although several theories have been fronted. Iceland. Another major center of shield volcanic activity is Iceland. Located over the mid-Atlantic ridge, a divergent tectonic plate in the middle of the Atlantic Ocean, Iceland is the site of about 130 volcanoes of various types. Icelandic shield volcanoes are generally of Holocene age, between 5,000 and 10,000 years old, except for the island of Surtsian Shield. The volcanoes are also very narrow in distribution, occurring in 2 bands in the west and north volcanic zones. Like Hawaiian volcanoes, the formation initially begins with several eruptive centers before centralizing and concentrating at a single point. The main sheet shield then forms, burying the smaller ones formed by the early eruptions with its lava. Icelandic shields are mostly small, symmetrical, and characterized by eruptions from summit calderas. They are composed of either thalliatic olivine or picritic basalt. The thalliatic shields tend to be wider and shallower than the picritic shields. They do not follow the pattern of caldera growth and destruction that other shield volcanoes do. Caldera may form, but they generally do not disappear. East Africa. East Africa is the site of volcanic activity generated by the development of the East African Rift, a developing plate boundary in Africa, and from nearby hotspots. Some volcanoes interact with both. Shield volcanoes are found near the rift and off the coast of Africa, although stratovolcanoes are more common. Although sparsely studied, the fact that all of its volcanoes are of Holocene age reflects how young the volcanic center is. One interesting characteristic of East African volcanism is a penchant for the formation of lava lakes. These semi-permanent lava bodies, extremely rare elsewhere, form in about 9% of African eruptions. The most active shield volcano in Africa is Nyamuragira. Eruptions at the shield volcano are generally centered within the large summit caldera or on the numerous fissures and cinder cones on the volcano's flanks. Lava flows from the most recent century extend down the flanks more than 30 kilometers from the summit, reaching as far as Lake Kivu. Erta in Ethiopia is another active shield volcano, and one of the few places in the world with a permanent lava lake, which has been active since at least 1967, and possibly since 1906. Other volcanic centers include Menengai, a massive shield caldera, and Mount Marsabit near the town of Marsabit. Extraterrestrial volcanoes. Volcanoes are not limited to Earth. They can exist on any rocky planet or moon large or active enough to have a molten inner core. And since probes were first launched in the 1960s, volcanoes have been found across the solar system. Shield volcanoes and volcanic vents have been found on Mars, Venus, and Io. Cryovolcanoes on Triton, and subsurface hotspots on Europa. The volcanoes of Mars are very similar to the shield volcanoes on Earth. Both have gently sloping flanks, collapse craters along the central structure, and are built of highly fluid lavas. Volcanic features on Mars were observed long before they were first studied in detail during the 1976 to 1979 Viking mission. The principal difference between the volcanoes of Mars and those on Earth is in terms of size. Martian volcanoes range in size up to 14 miles high and 370 miles in diameter, far larger than the 6 miles high, 74 miles wide Hawaiian shields. The highest of these, Olympus Mons, is the tallest known mountain on any planet in the solar system. Venus also has over 150 shield volcanoes which are much flatter, with a larger surface area than those found on Earth, some having a diameter of more than 700 kilometers. Although the majority of these are long extinct, it has been suggested, from observations by the Venus Express spacecraft, that many may still be active.